Good afternoon, students. In this lab, we will discuss and study about response of second-order systems and damping ratio. In preparing for Lab 5, you need to read about the Laplace transform, transfer function, and second-order systems. And Lab 5 report submission need to include the theoretical work on the derivation of impulse and step response for second order systems, your MATLAB simulation codes, all results including figures, comparing theoretical results and MATLAB results, and discussions as usual. The purpose of this lab is to study in MATLAB how the location of the poles and the damping ratio affects the response of a second order system. Variation of the damping factor zeta affects the value and the location of the poles that give rise to different system behavior. And the step and impulse response of the second order system depend on this factor zeta. Now, if I have an input x of t, as you know, I have this system, h of t the impulse response and yt the output. If it is a second order system, then the transfer function. Remember, in time domain, I have h of t, and in the Laplace domain, I will have h of s. And for a second order system, h of s, which is y of s over x of s, will be in general this form. Okay, this is one form of second order system. Omega n square, h of s is equal to omega n square, s square plus 2 zeta times omega ns plus omega n square, where omega n is the undamped natural frequency of oscillation, and zeta is the damping ratio or the damping factor. We can find the pole of the system by solving the quadratic equation of the denominator. You know this. If you see this, it is clear that it has two poles because this is quadratic equation, the denominator, and it has two zeros where at infinity, okay, at infinity. And the two poles of the system, after you solve this quadratic equation, you will have S1 given by this, you see, minus zeta omega n plus omega n, square root of zeta square minus 1, and the second pole minus zeta omega n minus omega n square root of zeta square minus 1. What's the difference? Here I have plus and here I have minus. So these poles can be purely a real number. For example, if zeta here, this is square root, zeta should be greater than or equal to 1 to have pure real number. Or it can be purely imaginary when the absolute value of zeta is less than 1, because when you do the square root, we will have square root of negative number, which will be j, there will be j. And it can be purely imaginary, or it can have real part and complex part. Okay, real part is this one, and the imaginary part is this one. Now, if we rearrange, now these poles are here, S plus P1 and S plus P2, like this. These are the poles. And if we try to factorize it to find the impulse response of this system, okay, we can do partial fraction. So this will be over A over S plus P1, A over S plus P2. And to find A, we can multiply this H of S by S plus 1 and evaluate at S minus P1. So if I evaluate at S minus P1, I will get omega n square over S plus P2, because S plus P1 will cancel here. on the left side, okay, and on the right side I will have only A, because this part will be 0. This method we studied it also in the lecture notes in ECEN220, okay, how to find A and B. Now A is this one, and if I put the values of P2 and P1, I will have this is A, and after cancelling omega n, I have A is omega n over 2 square root of zeta square minus 1, and B also omega n square this one, and I have omega n over 2 zeta square minus 1, which is minus 1. Okay, minus A. So what is the impulse response? Of course, the impulse response when we study causal system means a system with a region of convergence to the right, okay, to the right. So I will have A e to the power of minus P1t, B e to the power of P2t, everything times ut. And if I put the S, the P1, the P2, I will get this kind of expression, okay? Now this impulse response h of t, okay, can have different forms that we will see in the next that we will see below. Okay, so here in this part, what you will do, you will answer the following questions about the pole locations. Okay, one, what values of zeta results two poles being real? So you go to here, you see S1, you see S2, and you check which values of zeta will give me S1 and S2 purely a real number. That means we don't have imaginary part. Okay, so you can answer this. So you will answer this. What values of parameter zeta results two poles being imaginary? The real part is 0. So the real part completely 0, and I will have imaginary part only in the poles. That means, so again in the previous here, that means, so you look and you answer the second question also. And the next one, what values of parameter zeta result to equal poles? Same, you will see the poles and you will say zeta this and this. And the next one, what values of parameter zeta yields a stable system? A stable system, for a stable system, what should be the case? All the poles should be in the left plane, right? In the left plane, and the region of convergence should include the j omega axis. You remember this from the theory. And by looking at the S1 and S2, you can say something here, so you will answer this. And the next one, simplifies the equation, the impulse response equation 6, which is this one, okay? You simplify it, simplify equation 6 and derive the impulse response for 0 less than zeta less than 1. You will get very nice expression. So try to simplify it, and you will find a certain expression. Okay, simplify again the expression in 6, and in 7 derives the impulse response for zeta is equal to 0. Again, the previous expression, this expression again, you go and you simplify, and you get the impulse response for zeta is equal to 0. Okay, for zeta between 0 and 1, and for zeta 0, you will find and you will put the equation. That means here. Okay, these equations you will need it when you do MATLAB simulation, and when we compare the theoretical result of impulse response and your MATLAB simulation. That's why we need the equations. Okay, then you find the equations, and then after that, the second part, the second theory, step response of the system. So we finish the impulse response. What's the step response of the system? We know that it's the response of the system when the input is a unit step function, x of t ut. So the output of the step response, again using Laplace transform, what is y of s? X of s times h of s. So u of t, the unit step function, what is the Laplace transform? 1 over s. So 1 over s times h of s, which is above, and you will find this. Okay, this is y of s. This means the Laplace transform of the step response. That means if the step response is yt, and it is y of s. So how we get yt from y of s? Again, we do inverse Laplace transform. We know that this, and we do partial fraction. Now we have s also here in the denominator. Then y of s will become c over s, d over s plus 1, e over s plus 2. If you try to find c and d and e, I did it for you here. You can find easily. C is 1. You can verify this. D is minus of P2 over P2 minus P1, which is P2 and P1 are given above. And E is P1 over P2 minus P1. Okay? And for zeta greater than 1, if zeta is greater than 1, we say it is overdamped system. The step response of the system is given by this. I already gave you this equation. Okay, I simplify this one. After simplification, after changing to time domain, remember when we change to time domain, what is this? It will be, this one will be ut, c times ut, and this part d times e raised to minus p1 t. Yes, and this one e times e raised to minus p2 t. Okay, from the Laplace transform theory. Okay, it's like 1 over s plus a, 1 over s plus a e to the power of minus at ut. So that, like that, this will be c times ut. This will be d times e raised to minus p1 t times ut. This will be e times e raised to minus p2t ut. Then after that I simplify, and after I simplify I get this. If you see this expression, what is this expression? 1 minus e raised to zeta omega n times t cos hyperbolic, cos here, cos hyperbolic. In MATLAB there is cos function, the cos hyperbolic of a number. Cos hyperbolic of omega n square root of zeta square minus 1 times t, okay, minus zeta over zeta square minus 1, okay, e raised to minus zeta n times t, sine hyperbolic, okay. Don't make mistakes in MATLAB. It is not sine, it is sine hyperbolic, and this also cos hyperbolic. So there is a function sinh and cos in MATLAB, okay. Sine hyperbolic times omega of omega n square root of zeta square minus 1 times t. So you will get this, and the sine hyperbolic of the 1 in bracket. The same here, the cosine hyperbolic of the 1 in bracket. If zeta is less than 1, this is called underdamped system. And the step response, again I did it for you here, and the simplified form is this. Y of t is 1 minus zeta over the square root of zeta minus 1 minus zeta square e raised to minus zeta 1 n t sine omega dt, and again this cosine part, and if you simplify it you can also use this, where omega d means omega n square root of 1 minus zeta square, and phi is tan inverse of this over this. Okay, this is if zeta is less than 1, and if zeta is equal to 1, I have this formula. Okay, so for different values of zeta, I have an expression for y of t, which is the step response of the system. Remember this. Why we have this? We need it for the simulation part, because for different zeta you are going to plot yt, the theoretical value, and compare it with the simulation, the MATLAB simulation. The MATLAB simulation based on the impulse and step functions that we did in lab 2 or lab 2 or lab 3, second order systems. Okay, first order systems and about first order systems. Okay, now MATLAB simulation. This is the simulation part. Plotting the location of the poles of the system. Plot the real and imaginary part of the poles of the system for zeta 0, 0.2, 0.5. I give different values here, and omega n is equal to 1. So on the same plot, you plot for different zeta. Okay, for example, the poles. Okay, how you plot the pole 0 plot, the poles, you plot them, plot real of p versus imaginary of p, and here is the mark x. So you the x-axis will be the real part of the pole, and the y-axis will be the imaginary part of the pole. Okay, how do we get the poles? The poles can be found from the roots of the denominator. What's the denominator? This equation. Okay, so from the roots of this equation we can find the poles, and we will plot them, real part versus imaginary part, the imaginary on the y-axis and the real part on the x-axis. Here is the MATLAB simulation for one zeta, for example, for zeta 0.5. So that means I found P1 and P2 for zeta 0.5. How we can find? We can solve here, or we can replace in the previous equation for S1 and S2. But in MATLAB, it's very easy. We take the coefficients of this polynomial function. So the coefficient of S squared is 1. So we have 1 here. The coefficient of S, what is the coefficient of S? 2 times zeta times omega n. 2 times zeta, which is here. Zeta is given, for example, here, 0.5 times omega n. Okay, you can just put it zt. You don't need it 1. If it is a vector, if it is more than 1 zeta, you need to have 1 zt of 1, zt of 2, or whatever to identify the exact zeta. So that's why I put zt1 here. But you can take zt itself. So 2 times zt times omega n is the coefficient of S. And what is the coefficient of S power of 0? S power of 0 is 1. So the coefficient of S power of 0 is omega n squared. So I have omega n said. So you will list them in descending order, starting from the highest to the lowest. So the highest is the coefficient of S squared, 1. The coefficient of S next to zeta, omega n. And the coefficient of S power of 0 is omega n squared. So I make a vector A. I call this vector is A. So A is a vector consisting of the coefficients of for S squared, for S, and for S power of 0. That's it. So it is, for example, here a row vector 1 by 3. That means. Then we find the roots of the polynomial function. This how we find in MATLAB, using a function called roots. The roots of A. We just give the vector and we find the roots of A. And I will find P. So I will find how many roots? 2 roots, because that's quadratic equation. Roots of A. Then plot the real part versus the imaginary part. And here I say on the plot you mark as X, and K is the color. The color is black, for example. And grid on, you make the X level real of P and Y level imaginary of P. So I will show you here in MATLAB for this example. For example, I have here already for zeta 0.5. I have it already in a script file. I just run my script file. My script file here, lab5 v1. So I run it, lab5 v1, small letter, lab5 v1. Okay, see, this is a pole zero. The x-axis is the real of P and the y-axis is the imaginary of P. If you see, I have two marks. The two marks are the two poles. So if I want to know the exact value of the poles, I use data type here, what's the value here, and another data type, create new data type, another value here. Okay, so what is the value here? The x-axis is minus 0.5. The y-axis is 0.866. That means the first root is minus 0.5. Remember, the y-axis is imaginary, plus j 0.866. Okay, minus 0.5 plus j 0.866. And what about the second pole? The second pole is x is minus 0.5, y minus 0.866. The second pole, P2, is minus 0.5 minus j 0.866. Okay? So P1 is 0.5 plus j 0.866 minus 0.5 plus j 0.866, and P2 is minus 0.5 minus j 0.866. Okay? If you see here the y-axis here, if you go left here, you can locate it 0.866 for the y-axis here, for the y-axis minus 0.866, and the x-axis is a vertical line here minus 0.5. Okay, this is a figure. So you will plot for different zetas according to the questions and the lab report submission. Okay, these are, so if I call the pole the roots P, here I have it P is here. You see, one of the pole is minus 0.5 plus j 0.866. I and j are the same for MATLAB, you know, and P2 minus 0.5 minus j 0.866. Okay, this is the first about pole zero plot, and you will do for different zeta 0, 0.2, 0.5, 1.2 minus 0. Very easy. You just replace here. You just replace zeta here, and you plot on the same plot with different colors, and you can see their behaviors and how the location of the poles change when you vary zeta. And you have to give here the value of P1, the value of P2, the value of P3, like I did it now, the value of P4, P5, P6. P1 means for the first case, because I have here 0, 0.2, 0.5, 1. How many cases? 1, 2, 3, 4, 5, 6 cases. So this is the 6 cases. Okay. So in the for the 0.5, for example, for 0.5 you will write this one minus 0.5 plus j 0.866 and minus 0.5 minus j 0.866, like that. All right, now the second part. The second part is determining the impulse response of the system using the theoretical formula. Theoretical formula we derived in part 1, okay, above in section 1, and we compare it using the MATLAB simulation command called impulse. Okay, impulse for different zeta. Zeta 0.5 and 2, and omega n is equal to 1. Okay, so you will do only for zeta 0.5 and for zeta 2. You will plot the theoretical value and the simulation value on the same plot, and you compare them. Here, for example, I did, you see, zeta is equal to 0.5. And then I have the theoretical formula. The theoretical formula, which I get it from section 1, you will put it here. Okay, you will write the mathematical expression here. And what is B? B is the numerator omega n square, the denominator, the coefficients of the s square, s, and s power of 0 for A. Okay, for B, I have only s power of 0, so the coefficient is omega n square. So B is like this, A is like this. And if you remember from first order system lab, we have, how do we find the transfer function? H is transfer function B comma A. So B comma A. So the numerator coefficients B and the denominator coefficients. So this is the simulation. So H is then impulse. The impulse, I call the impulse function, impulse of H comma T. T is the time vector. So this is the simulation. This is the formula. Then you will plot what you get from the formula and what you get from this simulation on the same graph, and you have to get the same results. Okay, you have to get the same results. Please don't repeat this here and give me two graphs. I need to see this, because when I see the MATLAB code, I know that I check your MATLAB code and I know whether you put the correct theoretical formula in this part or not. Okay, so here let's go to MATLAB. I already did for zeta 0.5, so I go again to MATLAB. So let me close this figure. Okay, now here lab, I saved it here, clear all. This is again, I made a script file zeta 0.5, and then omega n is 1 and t is the time vector, and h of t, this is for zeta 0.5, I have here this expression. Okay, I have this impulse response, the mathematical equation. That means B is this, A is defined as this, and H is transfer function of B comma A, and H is impulse H comma T, and plot T H of T. H of T is the theoretical from the formula here, right, with black color, and the simulation is using the impulse command. Plot ATH with red color. So we compare the result of the graph from the theoretical formula here with the result of the graph from the impulse function, MATLAB impulse function. So the theory is black color, I plot it, and the simulation using the impulse command is red color. So I call this script file now. Let me clear here. Okay, what is the name of the script file? lab5 v2. So I will call here lab5 v2. Now you see this is the curve. The black and the red, they overlap. So that means I am correct. So as you see here, insert legend. If you see legend, so you have one black color, which is below here, and red color, the red on top of the black. So the black color is the theoretical result from the equation, from the mathematical equation. The red color is the result from the impulse function. Okay, the impulse, the MATLAB function. So the two are the same. So this way I proved that the theoretical, the mathematical formula is the same as the simulation. Okay, now you will do this, as I said, for zeta 0.5 and 2. Okay, you compare the theoretical formula and the impulse function. Okay, and the rest, these two, only using the impulse function. You will plot, use MATLAB to determine the impulse response of the system using the impulse command from lab 3. See, this lab 3, first order system, that means. So you, for zeta 0, 0.2, 0.5, 1, 2, and omega n. So you plot the results in the same graph onto using hold on. Okay, using hold on. Why we do this? Because we want to see the graph for different zeta. How does it look like? Okay, how does the impulse response behave for different zeta? Okay, the behavior. Okay, so that's why we plot them on the same figure. Okay, and here another one. So for zeta minus 0.2 and zeta minus 0.5, time is from 0 to 30. I will see each part. So please go in detail step by step for each part. Okay? So you will plot on the same graph. Okay. The third part, the last part of the simulation is the step response. So what we did for the impulse response, we will also do for the impulse for the step response. So we compare the theoretical result from the above equation as derived in section 2. Remember that formulas for the step response we derived for different zetas you see here. Part A for zeta greater than 1, part B for zeta less than 1, part C for zeta is equal to 1. Okay, or this is a theoretical formula. So we compare this with the step command. In this case, with the step command. Okay, because it's step response. Now the first part is for zeta 0.5 and 2. We do this, okay, using the formula and the step command. Okay, here is an example I have already here. Step response zeta 0.5 omega n1 time is here. This is a theoretical formula. For zeta 0.5, I have to select one of the formulas. Is it A, B, C from above for y of t? That means. So I put it here. And I define B here, A here, and transfer function here. Now instead of impulse, I will call the MATLAB function step. Step ht will give me the step response, and I get the step response, and then I plot the theoretical step response. Here, for example, I did it with black color, t versus ECT. Hold on, and on top of it, I will plot the simulation which I got it from the step command, and I compare the two. If I get the same result, that means I am correct. Okay. So I will show you here again a MATLAB example. I did it for zeta 0.5. I made here is a script file again. What is my script file? This is lab5 v3. I call it zeta 0.5 omega n1 time vector here. Here is the theoretical formula. ST, it's a long formula you see here. This is the theoretical formula for zeta 0.5. So I select from ABC from the theory, one of them that means. And I define B, A is here, and I call H is TFBA, and I call the step command S step of HT, and I will get the step response from the simulation. Then I plot the theory, plot T, ST, ST means this one, with black color here I did, and then with the red color I did the simulation on top of it, and I check whether the two are again the same. Okay, so I call what is the function lab 5v3. So let's see this is a plot. Again I see here two plots, one is below, you see the black color, and the red is on top of it. The black color is the formula, using the formula, the plot of the formula. The plot of the formula means this long formula that I got it from theory, from mathematics, and here using the step command. The red one is using the step command. You see here, and this is called the step response. If you see the step response after some time, after, for example, you see here after 10 seconds, the value of y of t is 1. Okay, because in the limit when t goes to infinity, y of t will be 1. The step response will be 1. You see here, so it is 1. But first it starts from 0 and go, and then it overshoots. This we call it overshoot. See, it overshoots, and then later it here this one is undershoot, and later it settles. Okay, this is the step response of the system. Okay, So this overshoot in some systems, it is not desirable. For example, if it is a speed, if you see here, how much is this one? Let me see with data tip. Yes, this is 1.163, means almost 16% of the maximum. So 16% of the maximum value here of the step, the step reference. This is my reference is 1. 16% of the reference value means it's a big overshoot. So it can, for example, it may not be desirable for the system. If suppose if it is a speed, for example, if this is one is, let's say it is one means 1 kilometer per hour, then I will have here 1.16 kilometer per hour as this time, which is not desirable. Or if it's an aircraft, for example, if it is if the reference is one is, let's say 1000 kilometer per hour, just example, and then this will be 1163 kilometer per hour, which is 1163 kilometer per hour above 1000, which is not good. That means, okay, so this is how we get the step response. All right, so take this one, part 2 and 3. What is this? Again, this one is you will do for different zeta only using the step command. Zeta 0, 0 0.2, 0 0.5, and please read and go through here this what is required from here, and also here for zeta minus 0 0.2 and 0 0.5. Plot the two results in the same graph using different colors, and give appropriate legend, XY level, and so on, and discuss the results, and so on. So always discuss the theoretical result in the MATLAB simulation, and please try to have the theoretical formulas try to derive by yourself, and try to compare the theoretical and the simulation result, and appreciate how the simulation can be done without complex mathematics equations. Thank you for listening to this lecture.